about this alpha and beta quadrants. So horizontal axis is phi and vertical axis is called as psi axis. Psi axis, phi axis. So allowed to low energy region, we have to always start from allowed region to low energy region. So if your structure has the amino acids lying in this and the residual amino acids present here are minimal, less than 5, then it is considered as your structure is standard. It can be used for the process of docking. So same here. So it is minus 62 plus 20 from alpha to beta. This line, this green line uses the track, and the blue line also uses the track. That here exactly this region, the amino acids should form. Here. If suppose your amino acids are not here, instead of that, here is the major chunk of your amino acids. That means it is in the disallowed region. It will be reduced and its structure, and it will also give an error value of 50 or 60. If it is 50 or 60, then it is better to not select that protein. You better go with the other enzymes or other proteins present in the disease pathway. The protein structure validation. So this is how the structure looks like. So this is how the in publications also we can incorporate these images. So in one of my publications, I incorporated this image. So here we can see the, sorry for the fonts which are very minute, we cannot see. Here it is going to give us the data. So whether it is in the allowed region, what is the percentage of amino acids present in the allowed region? It is around 87 here, it is on 87 here, it is 90 here. So that means my structure is good to go. I can go with this structure for the docking. If it is less than 70, less than 60, less than 80, I cannot proceed further with this structure. Now, applications of Ramachandran plot, validation of protein structure is the main key here. So validation has to be done, and improvement of the structure determination. If my structure is not good, I have to improve the structure by using methods. For example, NMR spectroscopy. We can go and dig into that and to understand what exactly the mistake is. Next, assigning the side chain effect of the protein backbone. So certain amino acids prefer to form a particular kind of secondary structure. So we have to also check for whether there is a secondary structure with your main structure of the protein. Whether it is there, whether it is hindering your Ramachandran plot, whether it is hindering the quality of the protein, that has to overrule before you proceed for the next step. Now I'm just going to give this screenshots of the software. So there are different softwares as I mentioned. IMOL, what it is used for, and Autodoc, what it is used for, Pyrex, what it is used for. So this is not exactly hands-on training. I'm just giving you the interface, how it looks like. So coming to the PyMod software is used for what? Energy minimization and preparation of the. So this is how the visualization of the ligand can be done. So this is how the ligand looks like. So it has to be downloaded, ligand has to be downloaded in STF format. Already that format has to be converted into what this PyMod does. Whatever STF file has been downloaded from your PubChem, that has to be converted into PDB file. That can be done using by this software called as PyMod software. Now it is converted to PDB file. Good to go for the next step. By using Pyrex software, I am going to demonstrate, not demonstrate exactly, I am just going to show you two different softwares, Pyrex and Autodoc, which is widely used software for this molecular docking technique. So Pyrex software is more easier to use, but it has its own pros and cons. The cons are nothing but the clarity of the image, as many students are nodding their heads. The quality of image is not that good when compared to Autodoc Vina. Now, what is the cons of Autodoc Vina? It requires some amount of learning curve, wherein you have to understand the coding. You have to do that in the command base. So we have to give some commands, which is very basic command. It is not that difficult also. But Autodoc Vina has its own advantage of clarity of images, right? But coming to advantage of Pyrex, it has inbuilt open barrel, it has inbuilt Ramachandran plot. We can do everything in the Pyrex itself. It has its own sub facilities. So this is the interface, very boring sort of interface of Pyrex. We have to just log in into, we have to just download the protein file as well as ligand file. So human candidate, the pancreatic alpha amylase and 1,2,3 benzenetrol. Both these are being downloaded here and they are going to dock here. It is not visible. So this is the protein structure. I'm just going to highlight where exactly this 1, 2, 3 benzene alcohol is being docked inside this. You have to trust me because it is not visible for you. You have to trust me whatever I'm telling. So the protein is present here and the ligand is present inside this ligand. It is having its safest pocket as we saw in that animation, wherein there is a protein and the dock pose or the docking will be done in the affinity. It is having its own affinity at that particular pose and side, it is going to dock. Now, how are you going to understand when exactly it is docked? It is very difficult to check by doing like this, right? So what we can do? We can convert protein into macromolecule and ligand into ligand molecule. This is then converted into PDB. PDB file is converted into PDB QT file using Pyrex software. So this is the beauty of Pyrex software. Each and every tool is present inside that. PDB is converted to STF is converted to PDB. PDB is converted to PDB QT, and we have to select an Autodoc Vina here, Vina wizard, right? So this Vina wizard is selected so that we can develop a grid box. We are going to develop a grid box. That grid box gives us idea where exactly the docking has to take place. So this is how the grid box looks like. As I was telling, nobody believed me. So this is where exactly the ligand is stored. Right? Now can you believe me because there is a grid box. Right? So this is the purpose of grid box, and grid box will be automatically fixed inside the Pyrex. But when it comes to Autodoc Vina, we have to select the grid box. We have to adjust the grid box as per our requirement. The binding affinities of the protein ligand. Once it is done, the binding affinity can be documented here. We can export this file as a Word file, wherein we are going to get this sort of affinity. This is what the scoring is called as. This is called the binding affinity of the drug. So the highest binding affinity here is minus 5.3. Is always in the negative. So negative higher number is always considered as the best binding energy. So in this case, minus 5.3 is the binding energy. Is it high? Is it standard? So technically, if it is more than 6, we consider it as a good docking energy or good scoring energy, which can be further continued into the research. But here, nevertheless, it is minus 5.3. This was just done for the demonstration purpose. It is 5.3. I can go with this, or I can reject this, or I can go with the next ligand, which is most suitable and has more binding affinity. So what it takes? Did I invest in anything here? Did we invest rows together? Did we invest time here? No. Now it is failed. I cannot select this as my ligand. What can I do? I can go again back. Within no time, I can go with the next molecule. I can do that. I can do trial and error. It is not going to hurt me. If I'm investing close together, what happens? If the same thing happened after that drug in the drug discovery process, it is going to hurt a lot. So that's why this is the beauty of using molecular docking, so that we can select or we can reject our proteins without having consuming much time. Now, moving on to the next result, that is Autodoc Vina, which is the most widely used software. I heard that it has been paid nowadays. I don't know, but I'm still using the free version. I don't know how. Maybe because I'm logging in. Now, preparation of molecules for the docking. So as I said, we have to prepare and we have to add some charges. We have to remove some molecules from the ligand or from the complex. We are going to add certain charges called as Coleman charges. So we have to go into this, select, and we have to add charges, and there are something called as addition of Coleman charges, which is going to help in the docking process. Now, this is what I was telling. The grid is not that clear as in case of Pyrex, but it is having a different color combination based on this. So we have to select the coordinates here 40, 40, 40, so that the box can be in the appropriate size, and it is going to give us the prediction where exactly the ligand is bound with the protein. This is where the ligand is bound with the protein. And these coordinates can be changed. If you want to increase the size, you can increase the size. Right? Now, docking of the receptor and ligand. So this is how the configuration notepad we can download these coordinates from the dock complex of Autodoc Vina. This is going to be documented. These are going to be our coordinates. These are going to be our scores, right? And in the table also we can download. So these are some of the configurations where in Autodoc Vina we can find. This is how the image generation. So it is much way better than the Pyrex software. When it comes to image generation, these are more clear, more interesting to visualize, and there are more options to change the 3D structure of the protein. So we can also have these images or these images or these images, right? So these are the coordinates which we can create in the Autonomina, which gives us feel of coding, but it is not exactly coding. Slightly there will be codes, even the commands has to be given in that DOS command. So that is where many of us, even me, initially had the apprehension that this is not for me. I am going to use only Pyrex. But Autonomina is way easier than Pyrex and generates more brighter and good images. Now results, this is how the results are obtained. So protein PDB-QT, and this is the center, and this is the grid box which we have sent, and the energy range and the exhaustiveness we can have this in this notepad. So this is how the binding energy. So upon doing all this, we get this table wherein the affinity is minus 9.1. Is it better than the previous one? Yes. So this was the second attempt using a different software, using a different ligand. I just docked into this. I got minus 9.1, which is excellent binding score. This binding score can be taken further for the research. It can be used as in case of in vitro study or in vivo study, and which can be proven as a drug. Right? So this is how without wasting much of your resources we can do. We can have a prediction. I'm not telling this is completely research. This is just going to give us prediction of 30 to 40%. Right? I cannot say if I'm doing this, I cannot say that it is a drug, it is going to be used for the treatment of cancer. That has a further steps involved in that. That is way more complex than this one. But of course, we have to agree this, that this molecular docking or simulations are going to be part of the integral part of the drug discovery process. Now, Discovery Studio Visualizer. So scaling of the results has to be done. So Discovery Studio Visualizer, this is the next software. What it does, it is going to give us a beautiful image of the dock complex, which can be visualized, which can be looked, and which can be taken into the publications. So this is how the results can be obtained. These are different structures. We can have 2D structure, 3D structures, and 3D structure in that the grid box can be changed, and the grid box we can clearly see what all amino acids are being engaged into this docking complex. Amino acids are very important, right? Hydrogen bonds are very important. What hydrogen bonds are involved in the docking complex? What are the amino acids which are being involved in the dock complex? And here it is much more evident that what are the van der Waals forces, what are the amino acids present inside this, which is the amino acid, which is the essential amino acid, which is going to be crucial for this particular docking, right? So this is how the scaling image quality looks like. And this is how the 2D structure look like. So we all can see the amino acids which are involved here, right? So it is all going to give us the confirmation of that. And this is how the publications demand. Nowadays publication, this is the quality of image which the publications are demand. So these are the references. So this was my attempt to make you understand basics of molecular docking and how it can be used in other fields such as pharmacology, not only pharmacology, even in therapeutics. A lot of pharmacy students are also there. Even you can use this. You can use this as a tool to understand whether this particular ligand has drug-like activity or not. I would like to show about the simulation results. I'm just going to just show the images, what all techniques I use in simulation. So this is my work, my PhD work. So this is how the binding score of my binding score is mentioned. This is how the structure looks like. So how to validate whether my dock complex is whether it is stable or not. So that stability can be explained by these techniques called as root mean square deviation. So this is only a protein. This is when it is docked with my ligand. So what are the fluctuations or what are the deviations in this? Where exactly the deviation is taking place? It is at this nanosecond of 80 to 90 nanosecond. Throughout my nanosecond of 100 nanosecond interval, which will take around 6 to 8 days to obtain this image or to obtain this months together sometimes. It takes months together. If you are running for 500 nanoseconds, it will take weeks to months together to generate these images, to check the stability of your dock complex. This is how my ligand, when it is bound with the protein, this is how it is stable. So that stability can be checked by understanding this root mean square deviation, which can be done by using the software called as GROMACS. GROMACS is there, many other softwares are there, which cannot be done in your normal computer. It has to be a supercomputer, Linux system, with which will cost, which is very costly also. I'm not going to discuss about that. Next is root mean square fluctuation. What is the fluctuation in your protein? Whether your dot complex has a fluctuation or not. So even that can be compared. So this is how your fluctuation can be understood in the 0 to 100 nanoseconds. Next is radius of gyration. So all these techniques, right? I'm not an expert in molecular dynamics. I'm just giving you an idea that how you can implement these dynamics and docking study into your own research, which is completely healthcare, which is completely a disease treatment. And hydrogen bonds. Hydrogen bonds are the most integral part, which is going to give us the stability of the protein as well as dot complex. There is something called as molecular mechanics Boltzmann area, which is going to give us the binding energy in kilojoules for mole. So this is how we can use molecular dynamics, molecular docking in our day-to-day research without wasting much of our. So if there are any questions, then the session is open for discussion. So is something called as MGL tools. So MGL tools has to be downloaded, and for that tools, DOS command has to be done. So that is a bit complex, but dynamics requires some learning curve. There is and even molecular docking also. There are courses for molecular docking which is months together. It's very difficult to learn molecular docking in one session. So it's very crucial to have your own practical application also. You should go and start with your practical understanding rather than understanding theoretically. So this was my attempt to make you aware of this. Many of you must be already come across this. Many of you must be expert in that. But considering the requirement of this activity, I wanted to explain about the initial basics of how molecular docking can be used in healthcare as a preclinical tool. Thank you. If no questions, I shall conclude.
Thank you, sir, for enlightening us on basics of molecular docking and its applications. Now I request Dr. Suresh Andani, sir, to present the certificate and memento as a token of love and respect.
our next speaker is on the way. Till that, we will have 10 to 15 minutes of break.